I believe I saw you at a SPECIF conference a few years ago. You've been to some SPECIF conferences. That's a space, oh for goodness, space propulsion, energy, and I don't know. Anyway, it's another group. A lot of NASA people and a lot of people in Los Alamos have been involved in that particular group. But they're a group that's open to a lot of the ideas that we're discussing here today. Particularly ideas about gravity, since they're interested in propulsion and things like that in those groups. And Pharis is the author of, are you 2 books or 3? 2, and they're both back there, and I encourage you to pick up a copy. They're interesting ideas. He's been at Los Alamos now for 30 years, is that right?
No, I was only there for 5 years.
Only there for 5. They kicked okay. Was a researcher at Los Alamos, the author of a couple of books, the latest one on gravity and ideas on gravity, is that right?
Well, and everything.
Everything, okay. Physics in general. This is the first time he's come to an NPA conference, although he's contributed papers before, so it's a great honor to have Dr. Pharis Williams.
Give me kind of a little introduction how I got started in this. I'm a retired naval officer, and when I got through in Vietnam, the Navy sent me to teach the safety, employment, and handling of nuclear weapons. Well, it wasn't there very long until my boss says, hey, I think there's something wrong with the safety, the numbers. And so I went to work and found that, yeah, all of the scientists at Los Alamos and Livermore and a couple of other organizations made a boo-boo. And that they had to go back and redesign some of the weapons. Well, the powers that be in the Navy sent me to the dungeon, which was teaching at the Naval Academy, teaching thermodynamics. Okay. Well, while I was there, I determined that there was significant problems with special relativity, general relativity, and quantum mechanics. And after I had found some errors in the nuclear weapons where supposed geniuses had done their work, it gave me the audacity to take on physics. So in teaching thermodynamics, though, one runs into a real problem, and at least from my point of view. So I went up and I conferred with Domina Spencer for a while. And after a while, she says, well, if you can't prove it, assume the opposite and see if that goes along with the experiment. If you can find an experiment that violates your false assumption, then you can see that the first is true. Now, I'll show you that here in just a second. Bottom is forward. Okay? Where all this pertains to gravity, though, is that in fundamental physics, Newton's gravity was always independent of his dynamic laws, his equations of motion. Same thing with Einstein. He tried to put gravity together with dynamics by curving the space. Well, even from Friesman physics, we know that one can talk about force-driven motion, or you can transform to a curved space and talk about motion as a function of geodesics. Well, that is essentially what Einstein did. But if you're going to throw away, or rather put on the shelf, Newtonian physics and relativistic physics, and think about thermodynamics, well, thermodynamics provide equations of dynamics caused by a force, and they also provide a gravitational law. Of course, they didn't teach you that in thermodynamics, so that's where we'll go here. And first I want to give you the premise, because if you have the fundamental laws tied up in thermodynamics, then those laws should tell you not only the dynamics, but they also should tell you the forces that you've got to play with. So you don't have to assume, like Newton did, a gravitational force. The law should tell you those. Okay, so here are the fundamental laws. The first you see is the conservation of energy. But note that I have 4 force terms. That's the 3 spatial forces, and then the thermodynamic force, which of course you can write in terms of mass density instead of specific volume. And that's where I went to talk with Dr. Spencer. Because when you're teaching thermodynamics, the first thing you do after you write the first law up there is say, oh, if I've got 5 differentials, then I better trot out 5 equations to have a solvable system. And the first equation that we always trot out is conservation of mass. Well, I have never seen a proof that mass must be conserved. And that's where I went to talk with Spencer, because I wanted to know, how can we prove mass must be conserved? And what she said is, if you can't prove it's conserved, assume it's not conserved and see what happens. If you find something that differs from experiment, then it must be conserved. Well, this is where the fun began, because if you look at the second law of thermodynamics, which is the denial of perpetual motion, stated like Cartesius did, that is, neighboring any state point there exists points you can't go reversibly, then you can do a whole lot of things mathematically that you can't do with the Clausius and the Kelvin statements. One of the first things you can find is that there exists an integrating factor for the first law, and that integrating factor is strictly a function of velocity. And from that, you can then obtain a path-independent differential, which everyone calls entropy. And there's where the fun begins, because entropy determines how the dynamics go, how it flows, time. It also determines the very stable states. That is, if you look at isentropic states, those are the most stable of all. And the other thing is, by looking at isentropic states, we'll find out the characteristic properties of fundamental particles. Okay? The first thing you do in thermodynamics, when you want to see what systems are doing, you look at the stability conditions. And you can write the stability conditions as a function of a whole series of families of variables. But if you write it in terms of the entropy, and here I scale the entropy so I've got another dimension, you write it in terms of entropy in space, you say, oh, that's well and good, but I need to have a variational principle to get dynamics. And the variational principle that comes to mind most readily when you have an isolated system is a maximum entropy principle. But my entropy differential is up here. And so I can't use this statement here to max in a variational principle. But I can parameterize this metric by saying it equal to CDT, where C is an absolute velocity, at which point the integrating factor vanishes. Okay? And now I can use the variational principle on the differential of entropy, and I find that differential of entropy squared in terms of geometry has a very funny looking relativistic like metric, which is really a generalization of the Minkowski space of special relativity, or even general relativity if you want to go there. But the important thing here is this geometry, there's 2 geometries tied together here. One, the differential change in entropy squared is 1 divided by a geometrical integrating factor times another arc length squared. Well, this one is path dependent and the entropy is path independent. The thing that ties the 2 together is an integrating differential, a geometrical integrating factor, which is called the gauge function, back from Hermann Weyl in 1918. Okay? And it's that gauge function that tells us a lot of what we wish to learn. One, if you look at the Weyl scale factor in the sigma manifold, which is energy, you find that the length of a vector at some point, final point, is given by the length of the vector at some original point, and then e to this line integral. if you look at isentropic states, isentropic state says that the length of a vector at the final point has to equal the length of the vector at the original point, and that's a condition that referred to as the Weyl unity Weyl scale factor. Well, if this condition has to be met, then that means that this line integral can only take on values that are quantized by 2 phi I n. Okay? Well, London showed that if one is given gauge potentials, in particular he used the electrostatic potential, and imposed the unity scale factor, then the only paths possible were those given by Schrodinger's wave equation. Okay, so this is where the quantization comes from. And the isentropic condition is what set up this quantization. And what London noticed was if he's given these gauge potentials and asked what paths are possible to end up with this quantization, you got quantum mechanics. But that's not where we need to go to find gravity. There's another question. Whenever you hit this line integral in the classroom, there are 3 pieces. There's basically the integrand, which is here the potentials. There's the path, which is the differentials, and then there's the answer. Well, what London had was the answer, and he had the potentials. He asked what paths were possible. But here's another question. What if we're thinking of a fundamental particle who has some characteristic that doesn't change as it moves around in space and time? Well, how do we describe fundamental particles? Well, they're charged. Well, that means also they may have mass. Well, if they're charged, then we have some sort of a gauge potential. So the question then becomes, can this equation tell us the possible gauge potentials of a fundamental particle whose characteristics do not change in space and time? In other words, the electron's always an electron, no matter where you find it. Okay? So now you go through this. Now notice we went to a 5-dimensional manifold. Maybe I should say 5-variable manifold, because some people like to reserve dimensions for the space we live in, and I think we live in a 3-dimensional space. So if we call these 5-variable fields, then here's the way the field metric looks like, and this is the set of expanded Maxwell's equations that must exist for this 5-variable field. You'll notice some of the Maxwell equations here, and then others get additional terms, okay? Then there's some new equations. Well, now remember what we wanted to know was what are the gauge potentials of a fundamental particle where those potentials don't change as we move the particle around. Well, it's a long ways and a lot of horrible mathematics to go from what we said on the previous page, this one here, to what the answer is here, okay? But look at that answer. This is the gauge potential. It goes as 1 over r, but it has 3 exponential terms here that we don't get in electrostatics. We don't get in gravity, normally, okay? This first one is, well, it turns out make this a non-singular potential. This will have a long-range force. It's 1 over r squared, but the force will go to 0 when r is equal to lambda n, and then it becomes the opposite. If it's an attractive long-range force, it'll become a repulsive short-range force. There you'll find some of the nuclear forces, okay? The other term here, this means that this potential is time dependent, okay? It's also mass dependent, but that's not as important as some of our experimental comparisons as the time dependence and this non-singular dependence. Okay? Here's what the fields look like. Remember we had that 5-variable field? These are the electrostatics. And this is the gravitational. And now here's our dependence upon space. That's that long range 1 over r squared. But notice here's where it goes to 0 when r is equal to lambda n. And this is what drives it back to 0 as r goes to 0. And of course here's our time dependence. I've left off the mass dependence because that's too weak to bother most of our discussion. Okay? One of the things that I've never seen in any theoretical exposition is how did the ratio of the gravitational to electromagnetic forces come to be? Well, those exponential terms, when you form the ratio of the forces, you end up with this, which is exactly what we've been seeing all along, but I know of no other way of predicting it. Okay, now let's compare the predictions of this to some of the existing experimental data. The perihelion advance, because it's non-singular, the advance is proportional to the lambda. Okay? And I can show what that is if anyone wants to see the math. Well, no. The redshift, well, it's exponential with respect to time and mass. That means that if you've got a very massive particle, the fact that the redshift is exponentially proportional to the mass, you can have quasars in a local galaxy with large redshift very easily that way. Okay? No Big Bang. If it's a non-singular potential, there's a point in time where you can go back and the universe will be static, and it will not be at a singularity. Dark matter, the time dependence that you see in that gravitational field means that if you're out in the arms of a spiral galaxy, and it takes several light years for the effective mass of the center of the galaxy to reach the position of that star out there, then the tangential velocity of that star in the spiral arm will not fall off like it would be predicted by Newtonian gravity. Because of time dependence, it will think that the gravity is much larger because it was older. And in the dark energy, there's a time dependence there also. And there's several factors that go into the dark energy, but the main one is the changing Chandra-Shekhar mass limit. They use the type 1A supernova because it supposedly has the same mass when it explodes. Well, the age of the supernova changes the mass it has because this is a time-dependent limit. And when you get and you look at all that, you find all of the data that they found so far is explained primarily by this and the fact that you have the redshift isn't exactly what you thought it was. But here's another one. Remember in the late 80s, early 90s, there were a lot of reports about a fifth force where people had gone down in submarines or in mines and found that the gravity they measured differed a little bit from Newtonian gravity. And then somebody went up on a big tall pole and said, no, it's the same. You guys are all full of it. And no one's heard anything about the fifth force since. So I had one of my students at New Mexico Tech go and check all this stuff out. All of the underground stuff show a difference. All of the above ground stuff show the same. And if you look at the non-singular gravitational stuff, which I have in the book there, you find that since the non-singularity changes gravity primarily below the surface, then that's where you'll see it in any experiments. And that's what they reported. Okay? Now here's some experiments that involve the inductive coupling. Obviously, if the gravitational field is in the same set of fields with the electric and the magnetic, then there's inductive coupling between the electric, the magnetic, and the gravitational field. And one of the first places this shows up is in the radiation pressure and energy density. When I first got to Los Alamos, I talked to their people in their laser department. We tried to get a way of measuring the energy density and radiation pressure accurately, more accurately than Nichols and Halls did. But even when I left there in the 80s, they still couldn't measure that energy density to better than about 6%, and that's not accurate enough. Okay. Here's another one. Because the radiation pressure is always a little less than the energy density, there is a point where you get, if pressure is zero, you still have a non-zero energy density. Well, my question is, how in the world is the empty cosmic distances going to support a pressure? You got, my notion of pressure is you have to have something there to push. Well, if it's a vacuum, then the pressure is zero, you'll still have a positive energy density. And one of my fellow professors at Naval Academy estimated what that temperature that radiation would be at zero pressure. It's a few degrees, 2 or 3, something like that. Okay. Here's another one though that will change the way you look at stuff. If it's inductively coupled, then you don't have an electric and magnetic. Well, right now we call them EM because they're inductively coupled, and a separate gravitational wave. What you have is a gravitational component along with the electric and the magnetic. The problem comes up though, we've always talked about transverse waves. You have a set of transverse waves and you have a set of non-transverse waves. That means you have another set of waves that you cannot measure with your linear antenna. Okay? So I designed an alternate communication system which was designed to convert transverse wave energy to non-transverse wave energy. That's the sending antenna. And then you convert non-transverse energy, wave energy, to transverse wave energy, and that's the receiver. Well, Northrop Grumman conducted the test to do that, except they didn't want to use the system I designed for them. They used an alternate, and they didn't get any results. Okay, so that's still an experiment to be done. The non-transverse waves looks everything like a neutrino. When you calculate the skin depth in copper for the non-transverse wave, it's like 10 to the 10 meters. Now, if that don't pass through your Earth, I don't know what will. Okay. The other thing is something as simple as an Earth's magnetic moment. If there's an inductive coupling, there's a charge-to-mass ratio, and it will predict the Earth's magnetic moment. And I think the prediction was 8.1 times 10 to the 22, and it's 8.6 or vice versa. So that's a pretty close prediction when you assume the Earth is homogeneous density when it may not be. And then Northrop Grumman hired Dennis Shurey to measure this inductive coupling, and he passed uncharged masses through a toroid coil, and he ended up measuring exactly what was predicted. And here's another one. A fellow asked me to look at the Earth's flyby anomalies. And if you look at the effective charge on the satellite interacting with the Earth's magnetic field, you'll find out that you'll predict exactly the type of velocity difference that they see in the flyby anomalies. Now, there's one other thing too. Einstein's field equations. Remember I said that I talked to Domina Spencer, and we said go ahead and assume that mass is not conserved, and we did the 5-dimensional stuff. If you assume mass is conserved, what you find is Einstein's field equations are the result of conservation of mass in a 5-variable field. Okay? That gives you 2 ways of doing gravitational stuff. If you want, you can do it this way, but I'd prefer to do it in regular old 5 dimensions where I get to choose the geometry and just assume mass is conserved. Here are the conclusions, and you can look those over, but basically what it means is thermodynamic laws provide you not only with the dynamic equations of motion, but they also provide you with the force laws that you must use. And it gives us predictions that compare with experiments that we've already done, and at least 2 that have new ones that have been done, and predictions for others that could be done, such as the fat photon, and another one that I'm wrestling with the patent office on a fusion reactor with whatnot. And for those that'd like to see a little bit of, here's the perihelion advanced equation, the lambda is gm over c squared. Complicated looking redshift equation, but you can see these exponential terms. There's one other thing about this. This ratio here says that there's a predicted difference in the redshift you get at the level of Hubble's telescope as you would down on the Earth's surface. So when my collaborator went back, talked to him at the Hubble telescope facility, and asked him about that, if we could get some data so we could compare this prediction, they said, we calibrated it all back to the Earth's surface. So any of this data is gone. It's tweaked away. Okay? In cosmological stuff, there ain't no Big Bang because the non-singular potential says, no, that don't happen. Here's the dark matter thing, and you can see that it looks just like the Mond stuff when you make the first order approximation. The dark energy looks a little more hairy and whatnot, but there's no need to talk about Einstein's constant or anything like that. And here's the time dependence for that Chandrasekhar limit on the 1A supernova. Here's that radiation pressure thing I told you about. Energy density is the sum of the squares of all 3 components. The pressure is the sum of the electric and the magnetic minus the square of the gravitational. But notice the energy contained in the gravitational is severely less than the energy in these. And that's why in the Nichols and Hull experiment you got such a low difference between the energy density and the radiation pressure. And here's your cosmic background radiation, that is 0 pressure, means that even though pressure is 0, you have a non-zero energy density. With that, I'll pause.
Good time for questions?
2.5.
Do we want to come up? Come to the mic? I think your work is fabulous, and I really appreciate it. And I just am curious now. These Newton's Maxwell's equations you came up with pretty early on. New version. Is that something you derived, or did you get that from somewhere else? I'm real interested.
I've never seen it derived any other place.
So, but I didn't see your derivation. Is that in? I don't.
It's in my. I didn't do it here.
Yeah, it's in your book.
Imagine there's a lot of math.
Yeah, but it wasn't in the paper
it's the
either.
second book.
Okay. I need to see that because that's very cool. Thank you for that.
Thank you.
Yeah, as an old military guy, I can relate to your background. I enjoyed the question, your presentation. Just to make a comment first, I recall in a briefing I took long ago about, I can corroborate that in terms of like the gravity discrepancies that you're talking about, because I was briefed on that a long time, well not too long ago, but moderately long time ago. So I do know that has been briefed in other circles, so I'd be interested in that. The second is that I'm wrestling with the 2 things you said, because you're dealing with thermodynamics, and that's my area as an atmospheric scientist. You used the second law of thermodynamics. I was wondering why when you used the second law of thermodynamics, you didn't use for an isolated closed system. Is there a reason why because the second law of thermodynamics talks about in terms of an isolated closed system, and you don't have that in your description?
I'm sorry, the second law of thermodynamics does not specify closed or unclosed. If you use it in the way that Carthy stated it, then you're not limited by the Clausia and Kelvin and Planck statements of the second law. When you get to the Kelvin and the Planck statement, you're typically thinking of a closed system.
Okay.
If you look at the Carthy statement, which is a little bit expanded on what I put there. That is, around any point, there are other points you can't go to reversibly.
Okay.
And that has nothing to do with closed or open or anything else.
Okay. So does that basically, maybe that gets into my second question. When you talk about isentropic and you talk about entropy, does that mean that you don't need to basically account for phenomena that we described as like enthalpy and Gibbs free energy and things like that?
It doesn't mean you don't need to account for them. I just haven't found a good way of presenting a useful thing. There is a mechanical enthalpy and as well as entropy also. Yeah. I just haven't found a way of experimentally detecting those.
Okay, thank you. I enjoyed it very much.
Thank you.